Here's the counterintuitive truth about industrial 3D printing. The hard part is not printing. The hard part is proving repeatedly that a printed part is the same part. Additive manufacturing is now an industrial production family, not just a prototyping trick. It can make polymers, metals, ceramics, composites, and even bio-adjacent structures. Yet most high-volume commodity parts are still cheaper and faster with molding, casting, forming, machining, or automated assembly. That tension between geometric freedom and production economics defines the frontier. Start with what industrial really means here. A qualified additive workflow is not a printer on a shop floor. It is design for additive rules, controlled feedstock, calibration, in-process monitoring, heat treatment or curing, surface finishing, non-destructive inspection, documentation, and a quality system that can sign off parts. If you skip those steps, you do not get production. You get uncatalogued geometry output. That shift changes the strategic question. It is no longer prototype versus production. It is uncertified output versus qualified manufacturing system. Many organizations can generate shapes. Far fewer can release load-bearing, end-use parts with traceable evidence. The second big finding is that additive manufacturing is not one technology. It is a bundle of process families, each with sharp constraints. Polymer extrusion behaves differently than vat photopolymerization. Powder bed fusion is different again, from directed energy deposition or binder jetting. Material jetting and inkjet-derived additive processes open other routes with their own trade-offs. Those trade-offs show up in build envelope limits, anisotropy, from layerwise construction, thermal distortion, and residual stress. They show up in surface finish and support removal. They show up in post-processing burden and in how hard it is to qualify a material and a process window. When leaders ask, "Can we print this part?" the real question is, in which process family, with what evidence, at what total qualified cost? Next, adoption is demand-led, not hype-led. Production use is strongest when complexity, customization, or consolidation matters more than unit cost. Additive wins when tooling is slow or expensive. It wins when you need internal channels, lattices, or integrated assemblies that are hard to machine. It wins when you cannot afford to stock spares, or when the tooling for an older part no longer exists. That is why you see traction in aerospace components, medical devices, fixtures, jigs, tooling, and selected end-use industrial parts. You also see it in consumer product cases, where customization or short runs can beat traditional tooling cycles. The common theme is simple. Additive manufacturing shines where the supply chain is the constraint, not just the geometry. A fourth finding is organizational readiness. Research has framed mainstream adoption barriers around the institution, not only the machine. Teams need training, shared vocabulary, and cross-functional workflows that include quality, procurement, maintenance, and cybersecurity. Without that, additive stays trapped as a lab capability or a prototype service, even if the printer itself is excellent. Design maturity matters especially. Many firms test additive by printing legacy parts designed for subtractive manufacturing. That approach often delivers the worst of both worlds. You keep the old geometry, and you inherit the new qualification burden. The compounding gains arrive when engineers design for additive from the start, using lattices, internal channels, graded structures, and part consolidation, and then co-design inspection and post-processing alongside the geometry. Now consider the biggest industrial bottleneck: qualification compression. Each combination of material, machine, orientation, geometry, post-processing route, and inspection path creates a new evidence burden. Even when the geometry file is identical, powder reuse history, environmental conditions, calibration state, and operator practices can shift properties. So the ambition is not print faster alone. The ambition is to cut the time and cost to qualify, without weakening assurance on fatigue, thermal performance, and failure modes. That connects to the next challenge: repeatability across sites. Distributed manufacturing only works if parts are equivalent across machines and facilities. Cross-site comparability depends on metrology, standards, and disciplined process windows. It also depends on shared definitions of what counts as the same part and who is allowed to say so. Materials research adds another layer. Industrial feedstocks keep expanding, including work on reprocessable polymer networks and experiments that use non-standard feedstocks to study print behavior. Yet each new material class reopens the same hard questions. Can you control properties over time? Can you prove aging behavior? Can you manage contamination? Can you certify it for the intended environment? Security and provenance are not side issues here. Additive turns CAD files, build files, slicing parameters, material lots, machine logs, inspection results, and release signatures into cyber-physical production assets.